I looked at one and the first one got 0. So that wasn't good.
Yeah, exactly. You had a fun party as well, Tom?
Sorry?
You had a fun party?
I don't know, as the others, I had a good time. The, yeah, I had like 30 people.
Oh, that's awesome.
It was quite busy and
I heard the party went very late.
yeah, so 6 to 12:30, I think.
Oh, that's pretty late.
6.5 hours.
That is a good party.
I was very tired at the end, so I was kind of falling asleep. And then Nick wasn't the last one to leave.
Wasn't.
Yes, which is unusual. Usually Nick is around and we like talk forever. Okay, so it's 3:10. So it's a pleasure to have Benedek Valko, who, if you, in case you don't know, he used to be a postdoc here at something. And the title of from UW-Madison, and the title is Pair Correlations for the Sine-beta process for even for beta.
Fine. So it's great to be back. I actually looked it up the first time I gave a talk at the Toronto Probability Seminar. It was almost exactly 21 years ago. Back then I was still a graduate student. It was up there.
It's insane.
Yeah, so this is joint work with a graduate student, UW, but it also builds on joint work with UW and Bali that actually started while I was here in Toronto. Right, so basic question in random matrix theory is, what can we say about the scaling limit, the spectrum of random matrices? You imagine that you take larger and larger random matrices, square matrices. You look at the eigenvalues, you have a larger and larger random set, and you would like to say something about the asymptotic behavior of that set. And there are a number of things that you can study. You can put a mass of 1 over n on each of the n eigenvalues. This way you will get a random probability measure, and you can study how this probability measure behaves in the limit. You can look at linear statistics, so you can take a test function and evaluate it at your eigenvalues, sum them up, maybe scale it, and ask what happens to this. Or you can look at the set itself, if there's some scaling, and try to see if there is some sort of a point process limit. And then in this talk, we will be interested in that particular object. So we will be interested in point process limits of the eigenvalues. So here is a sort of question. Okay, you want to study point process limit. How do you describe this limiting object, the limiting point process? So in what the classical
Hey, that's racist.
fair question.
No racism against Hungarians.
Yeah. So how can you describe the point process that you get at the end? And sort of the classical models, the object that they would study is the joint intensity function for joint intensity functions or correlation functions of the point process. So here's the rigorous definition, but it's basically like a generalization of the joint density. So you have infinitely many points. So looks at what is the asymptotic probability of seeing eigenvalues close to particular positions. So the first intensity function, or first correlation function, will just give you the density of the point process. First sort of non-trivial one would get the pair correlations of your process. So here is one of the classical examples in random matrix theory, the Gaussian unitary ensemble, where we can do everything. So the Gaussian unitary ensemble can be by taking a square matrix, you fill it up with IID independent complex standard normals, and then you just average this with the conjugate transpose so that you have a permission matrix in the end. So now you have real eigenvalues. So this is the Gaussian unitary ensemble. It's Gaussian, it has as much independence as you can sort of put into it. So it turns out that, and this is so sort of first sort of limit theorem in random matrix theory, that the big picture limit, if you just look at the empirical spectral measure, when you put convert the eigenvalues into a probability measure, you get this nice semicircle shape, Wigner's semicircle loop. And if you zoom in, especially if you zoom in the bot, so not at the edge of the semicircle, then you will have a really nice limiting point process, which belongs to the family of determinantal point processes. And it means that you can explicitly write down all the joint and intensity functions, and these will have this very nice determinantal structure. You basically, as an ingredient, you just need a kernel function, and that's basically sine x over x. And then you can produce the key joint intensity function just by computing a key by key determinant, where the entries will be this kernel function evaluated for all the pairs. So again, you have these nice formulas. These formulas actually show up when you study the asymptotic distribution of non-trivial zeros of the Riemann zeta function. So you have these nice connections to other areas of that. And then of course, when you scale, there's an extra freedom. You can choose essentially the local density. That's that parameter rho in all of these formulas. And you can choose this be your favorite constant. Often in the classical results, it's chosen to be 1, but in this talk, it will be chosen to be 1 over 2pi. Right, so why can we do this for the Gaussian unitary ensemble? Why do we have these nice results? Because you can explicitly write down the joint eigenvalue density of the finite matrices. And they will look like this with beta equals 2. So you have a von der Waals determinant raised to the second power. And then you have the product of basically normal densities next to it. And this von der Waals square will give you nice algebraic structure. And it turns out that because of that, you can just integrate out all the variables that you don't care about. And you can obtain those nice determinantal formulas. This is very special for this particular, so we need that second exponent on the van der Waals. Similar joint density functions show up from other classical random matrix models. So if you start out with real standard normals or quaternion standard normals, symmetrize them, you get the Gaussian orthogonal ensemble, the Gaussian symplectic ensemble. You will get the exact same joint density function, but now that beta exponent will be 1 or 4. You can still get formulas there. You can still do some computations, and you can actually derive the joint intensity functions, but they will be a bit more complicated. So just as an example, for beta equals 4, the pair correlation function in the limit will be given by this expression. Okay, it's still computable. It's sort of built from the same sin x over x function that we have seen the previous slide, but it's definitely a bit more complicated. And also, again, so beta equals 2, 1, and 4. Those are the cases that you get from random matrices. But if you look at this joint density function, you might ask, okay, what if I just put a general beta there and try to study the limit of this? There's no matrix seemingly in the background now. It turns out that you can show that again, there will be a point process scaling limit. This limiting process is called the Sine-beta process. It will be a nice translation invariant point process, but you will lose all the nice algebraic structure that you had in those previous 3 nice cases. So there are actually no known formulas that would work for all beta volumes. So how can we describe then the limiting point process? You can describe the limiting point process by describing its counting function, and there is a way to describe the counting function in terms of a system of coupled stochastic differential equations. You can also describe the limiting point process as the spectrum of a random differential operator, and I will come back to that in a couple of slides. And it really all comes from a model of Dumitru and Edelman. Again, a minute ago I told you that there's no random matrix in the background, but Dumitru and Edelman about 20 years ago, they found a random tridiagonal matrix, basically independent entries, that will produce this particular joint eigenvalue density for all values of beta. And then in a subsequent work, Edelman and Sutton, they looked at this tridiagonal matrix and said, well, if you want to understand the scaling limit of eigenvalues, you can try to study the scaling limit of the matrix itself. A random tridiagonal matrix is like the discretization of a differential operator. So maybe in the limit, you will get random differential operators. And they wrote down their guesses. And then eventually, the last 15, 20 years, all of these proved. The first one was soft edge scaling limit by Barint, Brian, right there. See. So the last 15 years, we learned a lot about general beta ensembles and using this random operator approach, but sort of a standard question at the end of these talks is always, okay, but can you connect this whole theory to the classical cases where we actually have formulas? How can you see these formulas from this approach? So the results that I will talk about will give a partial answer to this. We have a way of recovering the classical results for the pair correlation for beta equals 2 and 4. And in fact, we have a way of getting the pair correlation for all even integers. We don't have a way of doing beta equals 1 case, which is a classical case. And I will show you why it's important for us that we can only treat these even numbers. So we can describe the solution in terms of fairly simple ODE system and also give a Taylor expansion of the resulting pair correlation function. So this is the ODE system. So you need to solve an n-dimensional system. The coefficients will be given by these 2 bidiagonal matrices. So the first one is actually very simple. It's just like x times the derivative discretized. Second one might be a little bit more complicated, but it's still fairly simple. It only has quadratic polynomials in the entries. And then, okay, you take these for a particular n, you take these matrices, you solve this ODE on the complex plane. And once you can show that there is a nice unique solution that is an entire function in each of the coordinates, and then a particular projection of this solution will give you the pair correlation function for the sine-beta process, beta equals 2. Okay, so that's our formula, and we can say something about the solution. I will come back to this at the end. So here's a very short and quick overview of our approach. So the sine-beta process is a translation invariant process. So even though the pair correlation function has two variables, it's a two-variable function because your process is translation invariant, only the difference of the two input variables will count. So it's really a single variable function. Moreover, if you condition your process to have a point at 0, then you can just look at this condition process and just study the one-point correlation function, the density of this condition process. And this will give you the pair correlation of the sine-beta process. It turns out that this condition process is well understood, and it can be obtained as a limit of certain random matrix models. So we can describe the limiting point process. And we can also describe it again as a spectrum of a random operator and the zero set of a random entire function. And then studying this random entire function will give you information about the points themselves and the density of the points. That's how eventually you will get to these ODEs that will identify the pair condition. Okay, so that's the short overview, and I will try to now give you some background for all of those bullet points. But first, some history. It turns out that for beta equals 2n, people can compute a lot of stuff. So there are all these people who already worked on explicit formulas starting from the beta ensemble density. They can use Jack polynomials to find limits, not just for the pair correlations, but actually for higher level correlation functions as well. The formula is given in terms of these generalized hypergeometric special functions. Don't ask me for the definition. And so this right here, this screenshot is from Peter Forrester's book. You can look at the last formula on the bottom is the pair correlation for an even beta. It expresses the pair correlation function in terms of this 2n variable integral that actually has a von der Mond raised about 4/beta. Okay, so we don't have a way of connecting the two formulas. Certainly for certain questions, having an integral representation might be better than having representation in terms of an ODE, but maybe for other things, the ODE representation might be more advantageous. I personally was interested in this project because I wanted to see how the random operator approach can produce these classical formulas. But I think the representation that we found could potentially be used to say something interesting about these solutions. Okay. Right. Okay, so here are a couple of additional random matrix models. So we have seen the Gaussian ensembles. This slide introduces two other random matrix models. So the first one is called the circular beta ensemble. And again, it's just a von der Mond raised to a power, but now your points are on the unit circle, so not on the line. If beta is equal to 2, then this just gives the joint eigenvalue density the uniformly chosen n by n unitary matrix. The circular Jacobi beta ensemble is almost the same, but there's an additional term in your joint density. In fact, you can just look at this, and for particular parameter values, this is just the conditioned version of the previous ensemble. So if you imagine that one of those points, one of those endpoints on the unit circle is at position 1, then those are, and you separate the terms that have that point, then you get exactly the second ensemble. Okay, so again, for beta equals 2, this can be connected to classical random matrix models, and people studied this, but it makes sense to study it just for general beta, general delta. Again, when you choose that delta parameter that shows up in the exponent of the extra terms as beta over 2, then this is exactly just a conditioned version of the circular beta ensemble, conditioned to have a point position.
There's some problem that those aren't real numbers, but
So when delta is complex, then those two are paired up exactly so that they are conjugates of each other. If delta is real, you could just look at that as the absolute volume raised to the power of 2 delta, but it actually makes sense for complex deltas. But you have to assume that the real part of delta is at least larger than -1/2, otherwise it would be. Great, so Kilip and Nenchu basically motivated by the result of Dumitru and Edelman, try to find a nice representation for the circular ensembles that are basically the analogs of the random tridiagonal model or the Gaussian ensembles. And they work with orthogonal polynomial on the unit circle. They all work with Sine. So they knew about orthogonal polynomials in the unit circle. Here's one way to approach this using the theory of orthogonal polynomials on the unit circle. If you have finitely many points on the unit circle, you can put weights on these points to make them a probability measure. Once you have a discrete probability measure on the unit circle, you can encode that probability measure by looking at the orthogonal polynomials that they will generate. It's a discrete measure, so you have finitely many orthogonal polynomials. Just like on the real line, these orthogonal polynomials will satisfy a certain recursion. That's the famous Segu recursion that is included there. And the coefficients in the Segu recursion will be complex numbers with a length at most 1. These are called Verbolsky coefficients. And these Verbolsky coefficients will fully describe the orthogonal polynomials and then fully describe the eigenvalues and the weights. Okay, so that's basically a different way, change of coordinates. If you want to study points on the unit circle, you can study the orthogonal polynomials, and for that you can just study the Verbolsky coefficients. In the line, the analog of this is basically the same story, but then you will have this 3-term recursion for your orthogonal polynomials, and if you arrange the coefficients of the 3-term recursion, you basically get tridiagonal matrices. So that's why this is an analog of the Dumitru data. So Kilip and Nenchu looked at the circular Jacobi ensemble, and they showed that the Verbolsky coefficients for that for the random probability measure that you get from the circular Jacobi ensemble, if you assign Dirichlet independent Dirichlet weights, so they could just compute the distribution of the Verbolsky coefficients, and they could show that those are independent, compute exactly the distribution. So again, basically this way they got an analog of the Dumitru data result. So instead of say generating a uniformly chosen unitary matrix, you can now generate these Verbolsky coefficients, solve the recursion, and it will produce the eigenvalues. And then just a couple of years later, Bourgat, Nikekbari, and Roule show that there is a similar description for the circular Jacobi beta ensemble, so for the condition model. So it turns out that there the variability coefficients will not be independent. But if you modify them a little bit and you look at a transformed version of them, they will become independent. Again, you can describe their individual distribution. So if you're interested in studying the eigenvalues of random matrices, you can imagine, okay, I start with the random matrix, I somehow have to find the eigenvalues, so maybe I compute the characteristic polynomial first, compute the eigenvalues, and I take a scaling limit, and that's how I will get the limit. But in probability, if you study the limit of certain objects, and those objects come from a richer object, then it's natural to try to find the limit of that richer object, right? So it'd be nice to maybe find scaling limits these higher levels. So finding a scaling limit for random matrices that you started with, and then potentially you get scaling limits for the characteristic polynomial as well. And then you can study the scaling limit of the eigenvalues by looking at those limiting objects, random operator, random analytic function. So the last couple of years with Bain, a number of papers, we built a framework to do this when you have circular ensembles. So it turns out that if you have a probability measure, a discrete probability measure of a circle, and you study the orthogonal polynomials, you write down the Ségur recursion with the variables coefficients. If you look at that recursion, you squint your eyes, you can turn this into an eigenvalue problem of a differential operator. So the differential operator will act on vector valued functions, two-dimensional vector valued functions. It will be a very simple form, so just differentiate your function, you multiply it with this matrix 0, -1, 1, 0, which is really just a 2x2 representation of square root of -1. And then there's an additional term, a matrix value coefficient, that can be parametrized by just a path in the upper half plane. So it turns out that when you do this with the Ségur recursion, you get a differential operator of this form. And the path will be just a discrete path built from the variability coefficients. So if you start with a random probability measure, your variability coefficients will be random as well. And this path will be just a random walk generated by these random coefficients. So now if you want to study the scaling limit of your circular ensemble, you can study the scaling limit of the random walk. And it turns out if you understand the limit and you have control over how fast or in what sense you converge, then you can show that the operators themselves will converge to a limiting operator that will be built from the limit of these random variables, which will be just diffusion processes on the upper half plane. So with Bain, we did that for the circular beta ensemble, and we identify the limit as so the limiting operator was a random differential operator that was built from just a hyperbolic Brownian motion. That's just a Brownian motion on the upper half plane with an appropriate time change. And then the limiting point process is exactly the same Sine-beta process that you get from the Gaussian beta ensembles. And then the UW, we did the same for the conditioned version of this model, so the circular Jacobi beta ensemble. And it turns out that you get a very similar limit, but instead of a Brownian motion or hyperbolic Brownian motion, you will get hyperbolic Brownian motion with drift. So that extra delta parameter just shows up as a drift in your Brownian motion of the hyperbolic. Okay, but this gives a characterization of the limiting point process. So now if you want to learn something about the point process, you can try to study this random operator, see whether you can compute anything. Okay, so this is our differential operator. And now we want to understand how we can study the limits of characteristic polynomials if you have a limit on the level of the matrices. So if you just have a matrix, you can of course compute the characteristic polynomial as a determinant, right? So it's natural to guess that maybe you can do the same with your limiting operator. You can, certain cases, you can compute determinants corresponding to operators, unbounded operators. Here, if you look at the normalized version of this, so normalized in the sense that at 0, you want it to be 1, you would need to include the inverse of the operator. And what's nice about these differential operators that we work with, that their inverse will be just a very nice integral operator that will be bounded, Hilbert-Schmidt, so all of these nice properties. So even though the original operator is unbounded, which sort of makes sense because you have eigenvalues going up to plus infinity and minus infinity. When you look at the inverse, you can control it and you have a very nice description. So what ends up happening is that you can take sort of a regularized version of this determinant involving this inverse operator, this Hilbert-Schmidt integral operator. And then this is a well-defined object. It will be actually an entire function on the complex plane. The zeros of this function will be exactly eigenvalues of your, or 1 over the eigenvalues of your differential operator. And there are all these other ways that you can describe it. Basically, you can describe it as a solution of a shooting problem, starting from your differential operator and writing out the eigenvalue equation. You can use a Taylor expansion for this function, which sort of looks like a Fredholm determinant-like series representation. So there are all these nice ways you can describe now the limit of your characteristic polynomials, because you have this operator as well. And when you do this for those particular random models that we just discussed, the circular beta ensemble and circular Jacobi beta ensemble, then you can also describe the limiting sort of version of the characteristic polynomial as the solution of a stochastic differential equation system. So a one parameter stochastic differential equation system, and the parameter is the complex volume that you want to do your function. So the particular structure of this will be the following. You have this SDE and you don't really have to process what the SDE is. Once you have the solution of this SDE, this vector valued SDE, you take the two coordinates and you take a linear combination of these. And for that linear combination, you have to use an additional independent random variable with a particular distribution that will depend on the delta parameter. And delta is 0, so when you are dealing with circular beta ensemble, that extra distribution is just a Cauchy distributed random variable. And for general delta, it will be some generalized version of Cauchy. Okay, so now we can actually come back to the original problem that I wanted to talk about. So the goal of this whole talk is to show you how to use all this machinery to get actual formulas for the pair correlation of the Sine-beta process. So again, the first step is to know that if you are interested in the pair correlation function of the Sine-beta, then you can just study the density function of the conditioned process, to the process that you get from the circular Jacobi beta ensemble. So this HP is abbreviation for QRPCREL, because for the beta equals 2 case, that was the name that was used for this particular random matrix ensemble. Okay, so we reduced our problem. Instead of studying the pair correlation for sine beta, we are just studying the density for this QRPCREL process. And we have this representation of this point process as the 0 set of this random entire function. has this zeta function there. And then basically using the Stieltjes inversion formula, you can write down an expression in terms of expectations of the log derivative of this random function. And the result, so you take a limit, will be just the density of your point process. So this is basically because your entire function, essentially like a polynomial, is a product of these linear terms. When you take the log derivative, you just get individual contributions of those zeros. So when you do this inversion, you get exactly the density. So now, because my random function was the linear combination, the solution of this SDE plus this additional independent random variable, the goal is to compute that expectation, the bottom of the slide. Okay, so A and B comes from a specific SDE. Q is independent and it has a specific distribution. So it turns out that this is the part where we will have to use the fact that beta is an even number. When beta is an even number, then this delta parameter, which was beta over 2, is an integer. And the density function of this additional random coefficient will be just 1 over 1 plus x squared raised to some integer power. So really just a generalization of the Cauchy distribution. And in this particular case, when n is an integer, you can just compute the expected value in Q. So again, A, B, and Q are all random variables, but A and B are independent of Q. So if I look at that expectation, I can just first take the expectation of the Q random variable. And if you do that, you will get this formula with finitely many terms, which will be in terms of your random solutions of your SD. Again, if delta parameter is not an integer, here you will get an infinite series. So this part is really just a simple complex analysis residue computation. You actually need some additional information. So it turns out that we somehow the solution of the SD by default will give you some extra information about the size of the solutions. Because of that, you will know where the singularity is. Or in the appropriate computation, that's how you will get to that particular expression. So everything here is now just in terms of that SD that I showed you a couple of pages ago. So you can try to study that SD and see whether you can get explicit formulas for these expectations. And it turns out that, again, when this delta parameter is equal to n, and some sort of magic happens, and the ODEs that you get from your SDEs when you want to just follow the expectations, they will close. Okay, so basically you are just applying Ito's formula, take expectations, you get equations for those ODEs for the expectations, they evolve in time. But when delta, this extra delta parameter is an integer, these equations will close. And you can actually write down a system of differential equations. There's an additional added bonus that the original stochastic differential equation had some sort of nice invariance, scale invariance properties. So you can actually remove the time dependence from your equation. And in the end, you just get equations in terms of that Z parameter.
Where was that delta in the equations for A and B?
So delta was basically a drifter. So if you look at the very first part, so this delta shows up in the driving path of your differential operator as a drift. So originally it's just a hyperloop Brownian motion, and it's a hyperbolic Brownian motion between delta or I times delta. So the delta just shoots up there.
And must say, it's not very obvious that delta equals M special.
Yes, it's definitely not obvious. It really relies on, actually working with the SD, writing down the E2's formulas with these powers that show up there. And then it just happens that you have a system that proves this. Obviously, I'm hiding a bunch of technical details here. So that my SD starts from minus infinity. So you have to be very careful when you turn these SDs into UDs. You have to make sure that the expectations are finite. You have to make sure that you can exchange limits and expectations in various ways, but we have a good control over all these quantities. Because of that, we can actually make this precise. And once you do this, that's how you will actually get this UD system. So in this previous formula, we had basically two expressions: the log derivatives of this complex function e minus ib, which is basically just entire function built from the solution of the vector volume solution of your SD. And then there are other terms that correspond to sort of basically the ratio of the two coordinates. So once you do the computation, that's when you arrive to this UD system. So here you actually have n+1 equations. And just from the explicit integration involving this generalized Cauchy random variable, you get those combinatorial terms as the coefficients, and you get this nice expression for the 1-point function, the limiting point process. And it turns out that if you massage this a little bit more, then you can simplify it and get the formula that I advertised at the beginning of the talk. So again, these two matrices just come out of SD computations and bidiagonal matrices, so fairly simple structure. And in the end, this gives you an explicit formula for the 1-point function of the limit of the circular Jacobi beta ensemble, and then after this one step, after the conditioning step, the 2-point function of the Sine-beta process. Now, if you go back to those special cases for beta equals 2, it's really simple. It's just an intro to UD's problem to actually solve this. You can just solve the UD directly, and then after some algebra, you get exactly the sine kernel that you get from the Gaussian unitary ensemble. When beta is equal to 4, it's a little bit more complicated. UD, you have now 2 equations, but you can still solve it, and you can show that you get the limit of the Gaussian symplectic ensemble. If you try beta equals 6, then it will become more complicated. You can still get some sort of integral representation, but at that point, you have to decide whether that formula is simpler or the original UD is simpler. But there is another representation which is actually really nice. So if you just go back to the UD system, you can show that the solution will have a nice Taylor expansion around 0 that will converge on the whole plane. The coefficients, so these are now vector valued functions. The coefficients will be built from these 2 bidiagonal matrices. But if you look at the structure of the coefficients, they sort of look like the coefficients in hypergeometric functions. You have these in those hypergeometric functions, you have coefficients that are these rising ratios of rising factorials. If you squint your eyes, that's really a sort of like the ratio of a to some power and the rising factorial involving the matrix B. So this is a nice formula. For example, you can use it for approximations. You efficiently approximate the pair correlation function for a particular even number. You can also show that the first n-1 coefficients will be 0, which is something that you should expect if you know that you start from the appropriate Gaussian beta ensemble. So with the 2n exponent, the pair correlation function locally for small values should behave like x to the 2n, which means that in this expansion, all the terms before 2n should vanish. It turns out that that's a non-trivial statement. So if you look at these formulas, at least for me, it was not. We had to work with actual linear algebra and some combinatorics to show that all of those coefficients will disappear, even though we knew that they had to disappear. What we are again, so we have this nice expression. We are hoping that can be used for study asymptotic behavior and the other will give us new information about these coefficients. Again, unfortunately, it was this approach was very specific for beta equals 2n, and it also was very specific at the 2-point function. So the natural question is whether you can go to higher level correlation functions, but this trick will not work there anymore because you cannot do two different conditionings. If you condition of 2 points at 2 different values, the resulting point process will not be a nice point process coming from random matrices. At least I don't know any random matrix that will. But maybe there are things that can be saved and potentially can be used to attack that. Right. Thank you for your attention.